Okay. You're right. Let's continue. A few announcements just to begin. In terms of homework, the homework for the first 3 sections are actually up already. So 1.1, 1.2, 1.3. Not everyone has registered or enrolled in the course yet, so I put the due date for a week from now. So I think this is Monday, February 11th. This is also February 11th. And I believe this is Wednesday, or something similar.
What 1.2 or 1.3 are both at 13?
Oh, both of these?
Yeah.
Jeez. I'm so generous. Right, so just to make sure, so you have some time. The homework for this is not that bad. It's the kind of homework where if you get access the night before, you can handle it. So hopefully by February 10th or the morning of February 11th, you have access to the code. That being said, the class code is changed. So let me say something about that here. So the thing is, I updated the electronic version of the syllabus, so if you go online, you'll see this new class code in the syllabus. For those of you who already enrolled in the course with the old class code, you don't have to worry about it, because I moved all the students to this class before I deleted the other class. So if you already have WebAssign, you're fine. Anyone who's about to register for it, you should use this. And if you don't write this down now, just notice that in the syllabus that's on the class website, I updated the code. So the class code on the printed syllabus that I gave you on Monday last week, that's no longer valid. If you're newly registering after this point, you should be using this. And again, those who are already enrolled, don't worry about it. I already shifted all the students to that other class. This class has some defaults in it that it would just take forever for me to recreate on my own, so I decided to just put people all over here. Yeah, so homework is in about a week. Our first homework is due. We are pretty much done with this topic. We're going to just take a few more minutes. We should be done with this soon. We'll start this guy. I don't know how far we'll get into that guy, but we'll see. And as I said, the due dates, just keep paying attention to them because they will be dynamic. I'll shift them. If we're taking too long to cover something, I'll push it back or maybe move something forward. So just be aware of that. Okay. Let us continue then. We're still in 1.1. Last time we mentioned interval notation. So you should have that in your notes. You are required to use interval notation on this quiz, of course. So this is a topic that we're going to cover, but since you've already covered this topic in algebra, I guess we can kind of jump the gun here. I want to do some examples of finding domains, which we'll talk about later again, but it is something that you kind of should know how to do, so let's actually jump into it. And I'm going to want you to give me the answer in interval notation, so let's see how much you guys remember. Square root of x squared minus 4 and b so the first function is y equals that, the second function is y equals that. and write your answer in interval notation. See what we remember about domains. Okay, so who wants to explain to me how we find the domain of this? Yeah?
You would set it equal to 0.
Set what equal to 0?
You would set the square root of x squared minus 4 equal to 0.
Why would you set all that equal to 0? Explain your reason. Why would you do that?
Because I know when you find the domain, you usually set the equation equal to 0 and solve from there. You solve for x.
Is that what you always do? I mean, if I asked you to find the domain of this, like 3x cubed minus 7, what would you say?
Set it equal to 0.
You would set it equal to 0? Huh? What is this? It's a polynomial, so what do we know about polynomials?
The all real numbers.
All real numbers would work. The domain of this is
All real number.
minus infinity to infinity. Everything will work. You don't have to set it to 0, you don't care. Why do you set this to 0?
Because the factor is a radical.
Okay, what do you know about radicals?
Usually when any radical is over a 0, it's considered a
No, radicals are okay at 0. Yeah?
Negative numbers can't be inside a radical.
Negative numbers can't be inside of a radical, right? So it means if you have a radical, like n, and there's some function here, and this number out here is even, then the number under the radical needs to be greater than or equal to 0. That's how, and only if it's even. Now, if your n is odd, then pretty much anything will work. So anything that would work in the original function is going to work. So if this was instead that, now we need to set it equal to 0. That, all real numbers. Okay? We'll go over domain again. I just want to see how much you guys remember so far. Okay, so for an even root to work, and remember, when we don't write a number here, there's an invisible 2 there. Okay. So for an even radical to work, what's underneath the radical needs to be greater than or equal to 0. Being 0 is okay, but you need to be 0 or bigger, right? So when you see that, you're supposed to realize what we need is for x squared minus 4 to be greater than or equal to 0. So now, to solve that, you want to solve that inequality, and we know to solve inequalities, we pretend that they're equations. Right? So first, when we solve that, we can figure out, once we figure out where it's 0, we can figure out where it switches to either side of 0, right, by testing intervals. Okay, so we realize this is a radical. That means what's underneath, it's a square root. That means what's underneath needs to be greater than or equal to 0. To figure out that, I would set it first equal to 0. Now, if I set this equal to 0, how do I solve that?
Plus 4.
Plus 4 plus 6.
Right, you can factor. And so you get that x must be 2 or x must be minus 2. Okay? So that's where it's equal to 0, which means that's okay. Now, how do I know where it's less than or greater? Yes?
For example, if I know the answer is 2, but if I move the negative 4 to the other side, it's going to be 4, right? So I take the square root of each, so it's going to be x equals 2. Is that correct?
No, because you need plus or minus here. So you have to remember that.
Oh, yeah.
Yeah. In general, and again, this is something we'll talk about. In general, if something is not linear, the safest way to solve it is to factor one side, and we'll talk about the zero factor property. But yes, you could have moved the 4 over here, square root both sides, but then you have to remember to put the plus or minus in the event that the power here is even. Okay, so ultimately the answer is 2 and minus 2. What do we do with that?
Plug in and see which one is going to work.
Plug in what?
An x.
Plug in what?
Plug in the 2 and x and then see which one is going to work.
You check.
Yeah, check.
No, at 2 is where it's 0. Plugging in 2 is just going to give me 0. How does that help me? What do I need? I need for it to be greater than or equal to 0. How do I fix that? Yeah, guess and check what?
You substitute 2 for x.
Again, plugging in 2 for x will give me 0. I literally solved for that to happen. Yeah.
Anything 2 or higher would be greater than 0.
Okay,
So
you need to plug in numbers other than these. You need to plug in numbers in between these, not these. We know if you plug in these, you'll get 0. I literally just solved the equation to be 0. So what we have here is we can draw a number line. We can write the solutions on it. Now I know in the square root, being equal to 0 is fine, which means I can be equal to 2, so I'd write that as a shaded circle. And I can be equal to minus 2 and I can be equal to 2, so those are shaded circles. Now the thing is, I don't know where I can live with this regard. So what I have to do is not plug in minus 2 or 2, because that's going to give me 0, and I already know those are fine. I have to plug in things in between them. Yeah.
Yeah.
So I'm going to pick random numbers in between them. It doesn't matter what numbers you pick, so pick small as one. Don't pick like minus 1236. No, pick minus 3, right? Something that's easy to calculate. In between here, you can pick, for example, 0. It's pretty easy to calculate with. Over here, pick positive 3, right? And now you plug these numbers in here, right? So if you plug in a minus 3 here, this will give you a negative. This will give you a negative, which means overall there's a positive sign on this in this region. Plug in 0 here, this will give you a negative, this will give you a positive, and negative times positive is a negative. Plug in 3, this will give you a positive, that will give you a positive, so that will give me a positive sign there. I want you to notice that the actual values I do not care about, I only care about the signs, because that's all we care about, right? So I'm not wasting time actually calculating what the specific number is. I can just tell minus a negative number here, minus a number that's negative, right? And since 3 is larger than 2, minus 3 plus 2 will also be negative. I don't care that it's minus 1 technically, I don't care. I just care about the signs. So now we know that we need to be greater than or equal to 0. So that tells us that here is not going to work, because being negative means being less than 0. We saw that last time. But here, we are good, or here. So it turns out our solution is going to be this side and that side. So that's the diagram of what our answer would look like. What would it look like in interval notation? How do you write that in interval notation?
Open parentheses, negative, infinity. Negative 2, close parentheses, union, close parentheses, to infinity, open parentheses.
Right. So we can be equal to minus 2 or equal to 2. That's what these closed brackets are representing. Negative infinity means it can be anything less. Positive infinity means it can be anything greater. So that would be the answer. There's another way to look at this. X squared minus 4, right? If I look at y equals x squared minus 4, what does the graph of that look like? What does the picture look like?
Parabola.
It's a parabola.
Going down.
How does it look like this?
It would be
No,
shifted
it's
to the left.
shifted.
To the right, to the right.
No. Shifted how?
Down.
Shifted down,
By
right?
4.
By 4 units. So it's going to look like that. What's this going to be and that going to be? Those are the zeros, minus 2 and 2, right? Now, from the picture, you can immediately see where the positive sides are, right? You can see right away that the positive side is on the far right, the positive side is on the far left, but there's a negative sign in the middle, right? So whenever the thing you're looking at, you can have a picture for it. When graphing that thing will be easy, and graphing this should be easy. You don't even have to waste your time here with any unnecessary calculations. The picture will tell you the thing right away. So I know it probably looks like this. The positive sides are on the outer edges, so that's where the answer is going to be. positive. So this is when graphing is easy, right? I wouldn't do this with some complicated function. But with something like x squared minus 4, thinking of the graph is easy, when graphing is easy. And you see positive values on outer edges. And yes, we'll probably also have to talk about transformations of functions, right? Because if I had y equals x squared, some people suggested a shift to the left. What would a shift to the left make that function into? Right, if I wanted to shift 4 units left, what would that look like? Yeah.
Open parentheses, x squared plus 4, close parentheses.
Agreed? No, that's not right.
I would put it up 4.
That's an up. That's a shifting up.
So it has to be outside the parentheses?
What?
Outside the parentheses? The 4 has to be out.
No, the 4 outside the parentheses would also be wrong. The 4 outside the parentheses is actually exactly equal to that. The square would have to be outside. And were you going to say something? Okay, yeah, so things like that we need to, we're going to go over it, but you guys are forgetting more than you realize, I think. Yes, that's a downward shift. Yeah, let's do the second example. So this should go by a lot smoother since we just reminded ourselves how these things work. And we have radicals here as well. How do you solve that one? So indeed, domain. Yeah.
It's bigger than 0, right?
Come again?
You said the inside bigger than 0.
What is larger?
The
So we need 9 minus x squared greater than or equal to 0?
no, just greater than 0. Because it can't be 0.
Right. But not equal to 0 since it's in the denominator.
Yeah.
Right? Remember, we can't divide by 0. Jhevon's going to kill you if you do that. So ultimately, one thing we need is this is strictly greater than 0. Right? Coming
Top
up?
radical as well, 1 minus x. Has to be greater.
Ah. So now we took care of the denominator, but I want you to notice that in the numerator there's also a radical. Right? Which means making this guy fine, if that guy messes up, you don't have a function either. Right? So you still have to also worry about the top. So you have to realize you also need what to happen. Which one?
1 minus x.
So 1 minus x should be greater than or equal to 0. It's fine being 0 in the top, right? It's not fine being 0 in the bottom. So you actually have 2 requirements for this particular function. Okay, so let's see how to deal with those. Let's deal with one at a time. So if you have 9 minus x squared greater than 0, what's going to be the solution there? Tell me an interval notation. Bracket or parenthesis?
Bracket.
Remember, it can't be equal to. Then?
Union. Open parentheses.
X plus 3.
3. Comma infinity.
Okay. No. What's wrong? It's a valiant attempt. Thank you. But what's off here? What does the picture of this look like?
It's parabola going the opposite way.
It's a parabola going upside down. Because the x squared is negative. Which means where's the positive in this scenario?
In between.
It's in the middle. So this is where it's negative, right? In this case, the outer edges are the negative ones, right? You have to be very careful. You could also have gone through this and then tested values and you would have figured out the same thing. But this is, again, pretty easy to just look at the graph. 9 minus x squared looks like that. So this time the middle part is going to be what gives me the answer. So it's not this. In fact, it's in between. Okay. Be careful. So on the quizzes, on tests there's partial credit, but on quizzes there aren't. Right? You do your work on scrap paper and you only you only write your answer on the quizzes. And the thing is, I usually grade these with extreme prejudice. So if you miss a minus sign or something like that, you lose the point, no partial credit. And it's not particularly because I want to be mean. I want you to discourage making mistakes like this. You really need to pay attention to detail. It matters where the minus sign is. It matters a lot, right? So it's not like you shouldn't think of that as a small mistake. You really need to be thinking carefully through these problems. Okay, so that is where that part works. What about this part? Where does that work? How do you figure that out? What?
X is less than, right? Because less than or equal to
Right,
1.
you can add x to both sides, right? Or you can think of this as x is less than or equal to 1. So basically this is minus infinity to 1. Okay. So individually we know what's going on. How do we put it all together? What works then?
With the intersection.
You need the intersection. In this case, you need both of these things to work at the same time. One of the easiest ways to see the intersection is, again, to go back to the diagram. So now if we go to the diagram, for this one, we care about minus 3 to 3, and we know that we can be here. So we're in between minus 3 and 3, but we can't be equal to either. For this one cares about 1, and we can be equal to 1, but we have to be less than or equal to 1. So that would go back there and going all the way. Now the thing for this function to work, both the numerator and the denominator should make sense, right? Because if one or the other doesn't make sense, then the function won't make sense. So we need both of these to return a real number in order to get a real number. And so you just have to look at this picture. What region are both of them working?
Negative 3 and 1. Negative 3
Right here.
Yeah. Negative
Right?
3 and 1.
Because if you're over here, only one of them is working. If you're over here, only one of them is working. Only in this region are both of them working, right? So ultimately, what is the answer here?
All between negative 3 and 1.
Open parentheses.
Open parenthesis.
Negative 3.
Negative 3 and 1.
1 bracket.
That's the answer. Right, so knowing how to write down interval notation is usually just a part of the problem. A lot of times there will be some other issue going on that you have to solve that you ultimately express in interval notation. You have to know how this works. We will go over domains of functions, so if you're kind of sketchy on that, we will look over it, but I just want to see where you guys are with that. Okay, let's continue. Yeah, not much left to say here. I just want to give you basically a definition. Well, a couple definitions, and then we move on. We need to talk about absolute value. So there's a function that we call the absolute value function. And it is denoted by this notation, straight line bars with the x in it. This is called absolute value of x. The function is defined in the following way. Ultimately, what we want to do is this function measures the positive distance, or I shouldn't say positive, non-negative. So that means it could be 0 or positive distance between x and 0 on the number. A nice way to say this mathematically is the following, i.e., absolute value x is equal to the following. One of the nicest ways to look at it is as a piecewise function, where it gives you x if your x is greater than or equal to 0. In other words, if your x is already a positive number or 0, it's not going to do anything. And it will give you minus x if your x is less than 0. Now the point of that is if you have a negative number, it will take the negative of that number to make it a positive number. So what that does is give you the following. So this will say something like, for example, the absolute value of 0 is 0, right? Because the distance of 0 from itself is, there is no distance, it is 0. Absolute value of 5 is 5. Why? On the number line, if I measure the distance from 0 to 5, the distance is 5. Now you look to the absolute value of negative 5. Right? Now negative 5 is a negative number, which means this function is going to take the negative of negative 5. In other words, it outputs positive 5. And why? Because if I'm over here, then my positive distance from 0 is still going to be 5. It's just measured in the opposite direction. Right? The distance is still 5. So it always returns values according to this definition. If a number is already positive, it just outputs a positive number. If a number is negative, it takes a negative of it to turn it into a positive distance. This means that the graph is the following. So look at y equals absolute value of x. Now if your x is 0, it outputs 0. Now as long as your x is positive, it outputs x. In other words, y is equal to x when x is positive. So you just have the line y equals x on this side. So this is the line y equals x. Now on the negative side, it will actually look like that. Now if you continued with y equals x, this will continue here. What the absolute value does is it multiplies all these points by a negative sign to flip them up to make a positive value. And so we have y equals minus x as the definition on the left side. So absolute value of x, that function looks like a V, straight lines, making 45 degrees with the x-axis. And it's just y equals x on the right side, y equals minus x on the left side. There are other definitions of absolute value of x, but this is by far the most helpful definition in this class and classes beyond it. So let's give you some properties here. We'll be using it later on. Right now it's just the introduction. Allow me to introduce you to absolute value of x. He likes long walks on the beach. He's a very positive person. So here are some properties that will come in handy. For one, again, let A be any number, then turns out the absolute value of A is always going to be a number greater than or equal to 0. Absolute value of minus A is equal to absolute value of A. Absolute value distributes across products. So the absolute value of a product, you can think of it as a product of the absolute values. It also distributes across division. So the absolute value of a division is the division of the absolute values. And there's another important property referred to as a triangle inequality. It says the absolute value of A plus B is going to be less than or equal to the absolute value of A plus the absolute value of B. This is a very important statement. It's called a triangle inequality. If someone's lazy, they literally draw a triangle and write inequality. Basically, the intuition here, I mean, we're not going to see it too much here, but if you have something like this is basically something like saying, if you have some vectors, so if this has magnitude A and that has magnitude B, there is a concept of which you can add these vectors to get A plus B. And the triangle inequality is basically, let's turn this around. It's not going to matter, but so this will be A plus B, and this will also be A. So basically the triangle inequality is a fancy way of saying the shortest distance between 2 points is a straight line. Traveling along A plus B is going to be shorter than traveling along A and then B. And then that forms a nice little triangle right here. And like I told you, math people are horrible at naming things, so they're like, oh, there's a triangle, what should we call it? Triangle inequality? This theorem seems fundamental to the study of calculus. What should we call it? Fundamental theorem of calculus? it's just how they name things. Okay. So there's a pictorial thing that goes along with that, but it's a very, very important inequality. It's called the triangle inequality. And of course, here again, b is not equal to 0. You can never divide by 0. With this, there's a nice way to talk about the distance between two values on the number line. A, B on number line. Then distance AB. This is just basically, this is the distance between A and B. Is defined to be the absolute value of B minus A. Of course, it's going to be absolute value of A minus B. So for example, what is the distance between -2 and 3? Now intuitively we know this is 5, but it turns out you can figure this out by just taking an absolute value of the second number minus the first number. And in this case that just gives you 5. Which is 5. If you had done it in the other order, you would get -5, but that was still output 5. We're going to use absolute value more than that, but this is just the basic introduction. I also want to remind you of PEMDAS. Which, especially in a class like this, can cause you a lot of headache if you don't know it. What does PEMDAS stand for? Right. So this is it's a mnemonic to remember the order of operations. In which case, what that means is if you have some sort of mathematical expression and there's any ambiguity in how it should be computed, everyone has would agree that they should be computed in this way. So it's worth mentioning, it is a convention. There's nothing inherent in the mathematical operations themselves that say we should be computed this way. It's just a consensus. We all agree, okay, any ambiguity, this is how we're going to settle it. These are the rules to settle how we will do things in order. So that refers to the order of operations. That is the order in which we compute things. And it has been decided that PEMDAS will denote this order, where the P stands for parentheses. So if you have a bunch of things to compute, the first thing you want to do, figure out what's going on in the parentheses. Compute those first. Next thing is exponents, or powers. Next thing you want to do is raise stuff to the powers that should be raised to the powers. M stands for multiplication. D stands for division. I was going to say it's a conveniently forgotten fact, but it's inconvenient. You know those posts on Facebook where people type that expression and go, what is this? Is it -5 or is it 23? And everyone's like racking their brains. People often forget that multiplication and division have the same priority level in PEMDAS. It doesn't mean multiplication always comes before division. If both of them appear, you read from left to right. People often forget that rule. So here it's the same priority. If both appear, apply from left to right. That's because multiplication and division are very similar. You can think of division as just multiplication by an inverse. And so they have the same level of priority. So it's not like you always do multiplication before division. You do it from reading left to right, you do it in that order. Division is on the left, you do that first. Multiplication is on the left, do that first. Addition and subtraction are the last two, and they are similarly applied. Because again, we looked at this. Addition is just a moving to the right on the number line, while the subtraction is a moving to the left. They're essentially the same kind of operation. So this is addition and subtraction. And we have here. Okay. And that ends 1.1. Let's start at 1.2, where we're going to talk about exponents and radicals. So all that stuff we were talking about domain, we're going to discuss it now. Definition. An exponent or power is a number that describes repeated multiplication. In the sense, if n is a non-negative integer, then a raised to the n is equal to a times a times a n times.
No.
Here, a is called the base, n is called the exponent. Of course, this can be generalized for non-integer values of n. It's going to be easy to show you what they mean for fractions and negative integers, but for something like, what does it mean to raise something to a pi power? Then we're talking about advanced calculus. That's way above our pay grade. We're not going to even discuss that. But we're just going to assume this has some meaning, not necessarily that you can multiply something pi times. We extend the meaning analytically. We draw this for non-integer values of n. Yielding what we call the laws of exponents. So some of these I asked you about on the quiz, in the bonus section, to see how much you remember. What happened? What happened? Huh?
No, she was just asking.
I'd like to share that with the rest of you. Laws of exponents. Okay? So here's one law. X to the a times x to the b equals
A plus b.
x to the a plus b. Right? And the reasoning here is that if you have x to the a times x to the b, this just means x times itself, a times, and this is just x times itself, b times, and so in total you have a plus b times that you're multiplying x by itself, right? So once you kind of take this idea, you can extend it to multiplication, and this ends up being an addition in the power. Similarly, x to the a over x to the b is equal to
A minus b.
x to the a minus b. You subtract the powers, and that's because you have a bunch of x's here on top and a bunch of b's there, and you can cancel, and so what you've been left over with is all the top things eliminating all the bottom things, and you're left over with that. 3. Let's get some easy ones out the way. X to the 1 equals 1. Next, 4. X to the 0 equals 1, right? As long as your x itself is not 0. Okay? And why does that one make sense? Well, it's because 1 you can think of as something divided by itself, and by this rule, that is just x to the a minus a, which is x to the 0. Right? So it makes sense that x to the, something raised to the 0 power should be 1, and because this is the way we think about it, 0 is excluded. Right? So you'll see this rule in the book that, oh, we don't consider a 0. 0 to the 0 is meaningless to us because this kind of assumes that there's a division happening implicitly. Another rule, 5. Exponents distribute across multiplication. So they have two things being multiplied, raise it to a power. That's just this thing raised to a power, and that thing raised to a power. They also distribute across division. So remember from the very first lecture, we know powers, exponents do not distribute across sums, but they do distribute across multiplication and division. And to convince yourself of that, you can write it out like this, and you'll see that that's what things will be. you just write down x, y, a times. You can rearrange, group all the y's and group all the x's. You'll have a of each, and so you can ultimately end up with that. What is the other rule we want to do? What? X. Yes, x to the minus a. What does it mean to have a negative power?
1 over x.
1 over x to the a, right? The negative in the power does not change the sign. And again, why does this make sense? Because you're thinking there's an invisible 0 here. And then this means you have x to the 0 on top of x to the a, but we've already justified that x to the 0 is 1. So with a negative power, we'll have that. And again, we exclude x to be from being 0 here because of the division. 8. I think you have one left. The interesting one, the radical one. This is x to the a over b. What is that equal to?
B
I think it's
square root
square root of x to the
x to the
Right, the x to the a.
and b
a.
is
also
also
b. The b root.
yes.
Now, this is equal. Now, you can interchange them. Can be interchanged at will if your x happens to be non-negative. But otherwise, you'd have to worry about if this guy's negative, depending on what the b is. Now, one way you can remember that is a rule called, so here's a mnemonic for this. Here we go. There's a rule called flower power. That rule basically says, if you see x to the a over b, you kind of imagine that fraction as a flower, where the bottom is the root, right? So the b is the root because it's under the ground, and the top is the flower. It rhymes with power. So you end up with the a being the power, flower power. The bottom is the root, the bottom is the root. Okay. So that means, for example, if you see x to the 2/3, the 3 is the root. That's that. And you should also notice, because we're not going to be using calculators in our tests and quizzes, one way might be easier to compute than the other. Right? So as long as your x is positive or this is odd, you can interchange at will, and sometimes it wouldn't matter computationally which way you do. So for example, if you look at something like 9 to the 3/2. Now you can think of that as the square root of 9 cubed, or you can think of that as the square root of 9 cubed. Right? Either way is okay here because your 9 itself is positive. But if you're doing this one, you have to like 9 cubed. What's that again? You multiply it. No, it's easier to hear. You see that this is just 3 cubed and the answer is 27. It's much easier to see it that way. Right, so it's useful to know that you can interchange the order of the radical and the power once our base is positive or the root is odd. Oh, which reminds me, because a few people got this. Quite a few got this wrong on quiz 1. If you have 3 to the 4th versus minus 3 to the 4th versus minus 3 to the 4th. What was this?
81.
Right, that means 3 multiplied by itself 4 times. 3 times 3 is 9, times 3 is 27, times another 3 is 81. What is this one? Minus 81. What is this one? Positive 81. Why?
Because parentheses.
Because PEMDAS, right? If you're looking at this one, PEMDAS says there's some ambiguity here because you have a minus sign and a power. According to PEMDAS, you need to apply the power first. right? Because that's the P. The subtraction is all the way at the bottom. So you apply the subtraction after. So when you see this, you should imagine that this is happening. You need to apply the power first. Then you apply the negative sign. In this case though, PEMDAS says, work out what's in parentheses first, which is a negative number, and then you raise a negative number to an even power that makes it a positive number. So careful of those little mistakes there. Quite a few people make mistakes there, more than should make mistakes there. Sometimes you have mistakes, and then sometimes it's kind of weird that this mistake is happening. This happened often enough that it started to strike me as weird. Like, why is this strange? This is like the 8th paper I've seen this on now. Okay. What else do we want to talk about? Okay, so now the last rule that I erased is a nice segue into the discussion on radicals. We'll get back to some more examples last time. Now a radical this is x to the a, where a is a non-integer fraction. So these are basically radicals are when you have powers that are fractions, right? There's a principal definition, the principal root or radical, but you can extend this. It's defined to be x to the 1 over n, right? Where n is just some integer, some positive integer. N greater than 1 is an integer. Okay. So example, x to the 1/2, x to the 1/7, x to the 1 over 13 are radicals. And more generally, you can think of anything to a fractional power that doesn't reduce to an integer as a radical. More generally, right? These are more like called the principal radicals. But you can, more generally, you can call any such thing a radical. So you have x to the 2/3, x to the 7 over 11, x to the minus 3 over 5. These are all also considered radicals in a more general sense. And now we know what these mean. So, i.e., I'm really referring to the fact that x to the 1 over n can be used with this notation, where there's a power of 1 here that's not being written. Now, it is worth mentioning that the domain, talking about the domain of this function. So you need to remember, as a rule, this is the number that needs to be multiplied by itself n times to get this. So, for example, the square root of 4 is equal to 2, right? Because here you have a 2, and you need 2 squared, which means that's the number that you have to multiply by itself 2 times to get to that 4. Now that being said, if you multiply 2 negative numbers here, you will get a positive number. And so what ends up happening when there's a square root is that you can never really have a negative output. And so this idea leads to the domain of this function. So you want the domain of an expression that looks like this. This is going to be cut in two. And it's going to depend on if n is even, because if you're multiplying a bunch of even things, you'll always get a non-negative answer versus if n is odd. So because if n is even, you'll always get a non-negative answer. Only the non-negative outputs are allowed here. So that means 0 to infinity. Or in other words, x needs to be greater than 0 or equal to 0 for that to work. If n is odd, then it doesn't matter. Anything here will work. You can think of that like something like the example here. Something like the cube root of minus 8 is actually a negative number. It's minus 2. It's defined. That's a thing. Minus 2 times minus 2 times minus 2 gives you minus 8. So if you have an odd power and a negative, don't worry about it. It's still going to work. Even power and a negative doesn't work so well. Especially since we don't have complex numbers at our disposal here. So for us, something like the square root of negative 8 is undefined for us. What else do I want to say? Let's talk about some properties. Maybe we can do some examples. I know all this writing is probably getting a little bit boring, but please pay attention. As our domain example showed, you don't remember as much as you think you do, so pay attention. I got this. You know how to find domain? I know how to find domain. Who do you think you're talking to? I mean, it's through algebra. Well, you guys didn't really know as much as you think you know, so try not to be bored, pay attention. And these aren't going to be too insightful because we know better now that radicals are powers. So most of these are going to be like duh, but we have to be aware of what works. So the idea that you should know, radicals distribute across products because powers do. Radicals distribute across division because powers do. You can stack radicals because you can stack powers. So you can have something like the mth radical of the nth radical of A, and this can be thought of as the nth radical of A. And that's because you can think of this as x to the 1, a to the 1 over n, and then you raise to a power of 1 over m. You can multiply the powers to get 1 over n times m, which now translates to this. Yeah, and one other rule. If you take the nth root of a to the n, what do you get? It turns out that there are two possibilities for this. You can get a in what case?
If n is positive.
No.
The square.
No, more general. A little bit more general than that. If n is odd, it gives you a. What about if n is even? What do you think it gives you?
Plus minus.
Hmm?
Plus minus.
What kind of? Well, let's think about it. Let's choose an even example. Like the square root of 2 squared is what? So 2 squared is 4. Take the square root of that, and you get 2. Okay. What if I took the square root of minus 2 squared? What is that? Huh? It's still 2. Right? So notice that if I input 2, I get 2. If I input minus 2, I again get 2. What does that remind you of?
So long as it's
Absolute value.
Absolute value. So now, in fact, an alternative definition of the absolute value function is precisely that. So there are several places who would define this function as just the square root of x squared. So you should know that's also another definition, and this does show up from time to time where thinking of it this way is useful, but you should know the piecewise function definition of absolute value x also, because that's also very useful. In fact, I think in more cases than not, you would find the piecewise definition more useful than this. But this does come up. So you should know if you have an even radical on top of an even power, you're actually getting some absolute value. That will always return to a non-negative number because you're raising this to an even power, so it's going to kill any negatives there. Let's take a break from definitions and let's actually start simplifying some stuff. So simplify / combine the following. A. I probably won't get through all of these, but you can try them for next time. Assuming here that A and B are greater than 0. I was hoping we could get to this one. This was actually on the quiz. Okay, rationalize a silly example. Just to make sure you remember how to do it. On the bottom is radical or Let's do that first, just because. Okay, who think they got this one on their quiz? It's going to remind us of a very important simplification technique. Yeah?
I tried rationalizing the numerator.
Rationalizing the numerator, and how?
I multiplied h from the top term, x plus h minus x, in parentheses.
What do you mean multiply h from the top term? I don't understand.
Like,
Like from that, what did you write down after that?
I wrote x plus h minus x on the top term. And the denominator will be h times radical x plus h minus radical x.
Okay, how did you get there?
I multiplied the numerator
By what?
by x, the whole term, x plus h, radical x plus h, minus radical x. And the same thing with the denominator.
Okay, and what? Okay, so that's what you did, and you got this. Here's that, if you multiply this out, you would get that. Because basically, what do you have in the top here? In the top here, you would have the radical of x plus h minus radical x times the radical of x plus h minus radical x. In other words, that is the radical of x plus h minus radical x all squared. What do we know about that expression? What does that expand to? That was also a quiz problem technically. Right? Where we have a minus b all squared or x minus y all squared. What does that expand to?
X plus h.
Like if you have a minus b all squared, what do you get?
A plus b minus b.
A squared minus 2ab plus b squared.
Okay, that's what you should get. Okay, so that's what you have here. Now if I apply that rule here, what would I get? I would get this squared, which is the a, so that's just x plus h, minus 2 times this times that, radical x plus h, plus this squared. That's what I would get. I would not get that. So there's an error here. What's the error? Yes? Okay, never mind. What's the error? Yeah.
Wouldn't you multiply by the conjugate? So
Multiply by the conjugate. That's the key phrase. And what's the conjugate?
it will be the same thing, but you switch the negative sign to a.
Why? Why does that work?
Oh, because it cancels out.
So say you're in a quiz and you don't remember. Do I keep the same sign or do I change the sign? How would you figure out which is which? Well, I mean, you could just write this down, but well, keeping the sign is not going to work because I get 3 terms and it's not going to work. But why did the positive sign work? There's a rule here that's hidden. What's the rule? Why change the middle sign? What's the rule? What's the buzzword? What's the key phrase here? Yes?
Difference of squares.
Difference of squares. That's why you change the middle sign. Look at what you have here. Let's say, again, call this A and call this B. What you have here is A minus B. What you have here is A plus B. You would choose to put a plus, you would choose to say, change the sign, because what's going to happen now is that your numerator is going to look like A minus B times A plus B. And what does that multiply out to? A squared minus B squared. It's the difference of squares formula. So that just tells you square the first thing minus square the second thing. So again, there's a reason why I'm giving you these rules starting from the very basics, starting from scratch, and tell you know this formula so that you can see it anywhere. Because they're going to help you. When things look complicated, there's always a simple rule in the background working. And you need to be able to recognize that. And that's going to prevent you from making silly mistakes. You'll know that I need a plus sign here because keeping the sign is not going to eliminate what I want. It's going to keep a radical there. Right? You multiply, and this is called the conjugate, this expression here. This is called the conjugate. Of the first one. By the way, these are conjugates of each other, so I can think of this as the conjugate of that and this as the conjugate of that. I also want you to know that a conjugate doesn't just mean you'd have two terms and change the middle sign, because if this were a cubed, your conjugate would actually have three terms. Y. Again, there's a hidden formula of y. Then if this was a cubed, you'd want to cube each side, so you should be thinking difference of cubes formula. You'll remember that the difference of cubes formula, if you have a cubed minus b cubed, that's just a minus b times a squared plus ab plus b squared. In other words, this is the conjugate of that expression if we had the cube root, right? There's always a hidden formula. It's very important that you pay attention to the rules. I know they seem basic and simple, but really they are everything. Everything in this class, no matter how complicated, there's a simple rule why it has to be that way. And if you really know the simple rules and you really apply them, then everything's going to be fine. We'll stop there. We've technically actually completed this section. We're going to finish up these examples, but there's nothing else to teach for 1.2. And then we'll start on 1.3. But try these examples on your own, and we'll start the class.
Yeah. It's this one.